Good morning, class. We are looking at practice test number 3, module 3, covering chapters 5, 6, and 7. Here's 6.3 inverse trigonometric functions. And chapter 7, trigonometric equations and identities, also known as analytic geometry. Find the exact value of the expression and justify tan inverse of tan of negative 2 pi over 3. Reminding everyone of a few things as far as the inverse functions are concerned. Remember, all trigonometric functions are periodic. None of them passes the horizontal line test. None of them has an inverse unless you do the restriction. So the restriction that we did for sine was to put that between negative pi over 2 and pi over 2. And it does have an inverse as a result. Domain becomes range, range becomes domain, and for example, f of f inverse of x becomes x, the composite function. In this case, sine x, this x belongs to sine, must be between negative pi over 2 and pi over 2. In this case, sine inverse of x, this x belongs to sine inverse, must be between negative 1 and 1. For tan inverse, the restriction is similar between negative pi over 2 and pi over 2. The endpoints are not included in the case of a tangent. In the case of a sine, they do exist. Okay. And so cosine, the restriction, we put it between 0 and pi because we want to cover the entire range of negative 1 to 1. Cosecant basically follows the sine because it's 1 over sine. And of course, y can't be 0 when you do that restriction. Secant follows cosine because it's 1 over cosine. Y can't be pi over 2. Cotangent does not follow tangents because of the graph, if you recall, looks like y equals x cubed, negative x cubed, and it goes from 0 to pi, one complete cycle, in order to have a continuous function, so 0 to pi. Okay, so that's the idea, everybody. And so when you look at tan of negative 2 pi over 3, it's in quadrant 3. And when you have the circle, so clockwise makes it negative. That's the same as tan of pi over 3, because in quadrant 3, remember, the period for tangent is pi, and tangent is positive in the first and third quadrant. Okay, therefore, tan inverse of square root of 3, because tan of pi over 3 is square root of 3, and that gives us pi over 3. By that, you can write this one when you get this far, of course. Tan inverse of square root of 3 is theta. By definition, tan of theta equals square root of 3, which gives you pi over 3. So it's very straightforward. All right. Secant inverse of square root of 2, what is it? Let's call it alpha. By definition, secant of alpha becomes square root of 2, and we may not remember trigonometric functions of secant. We know secant is 1 over cosine, so the reciprocal of that, which is 1 over square root of 2, or we should know it's square root of 2 over 2. And alpha becomes pi over 4. It's one of those common arcs. Cosine inverse of 1/2, set it equal to alpha, beta, gamma, x. Choose any variable of your choice. By that, we mean cosine theta equals 1/2. It's a common arc. The answer is pi over 3. Tan of cosine inverse of square root of 3 over 2. So we're going to work on that. So we let cosine inverse of square root of 3 over 2 be something, for example, beta. If so, by definition, cosine of beta becomes square root of 3 over 2. And that is a common arc. Beta is pi over 6. So we are looking for tan of pi over 6. Tan of pi over 6, which is square root of 3 over 3. Cosine of cosine inverse of 1.2, it's undefined because 1.2 is larger than 1. A couple of ways to look at that when we look at cosine inverse. We are looking at this case, everybody. X is between -1 and 1. One other way you can handle it, say, okay, I'm going to solve it as follows. Okay, let this, I'm going to write it here. Let cosine inverse of 1.2 be alpha. By definition, cosine alpha equals 1.2, and this has no solutions, everybody. So we should know that this is another way of approaching it. Either way, no solution, undefined. I want to find the exact value of cosine of sine inverse of -1/3. And we are going to look at two methods. You don't have to do both. I just want to remind you. So please understand that this is an angle or arc. So let theta represent that. So you're looking for cosine theta. So first, we need to understand what we want to do. So according to this, sine of theta must be -1/3, which is negative. And when you look at inverse functions, there's a unique answer. So it's not that we're looking for, remember, from 0 to 2 pi, there are two answers if sine theta equals -1/3, for the sake of being unique, because we're talking about inverse. We remember the restriction is from negative pi over 2 to pi over 2, okay? And sine is positive in the first quadrant, and in the fourth quadrant, of course, negative. Therefore, it belongs to quadrant 4. In quadrant 4, x is positive, y is negative, and sine is y over r. So sine is y over r. Y becomes -1, r becomes 3. Y is x2 square root of 2 because x squared plus y squared equals 9. So let me show you. X squared plus y is -1 squared, you get +1. R is 3 squared, you get 9. X squared becomes 8. X is square root of 8, which is 4 times 2, which is 2 squared root of 2. That's how you arrive at the answer. Well, cosine is x over r. So cosine is x over r. So we have all the sides. Therefore, it's 2 square root of 2, which is x over r, which is 3. So that's using circles. If we want to go with identities, we use Pythagorean identities. We remember that. When we have sine squared plus cosine squared equals 1, we should know, for example, sine squared is 1 minus cosine squared. Cosine squared is 1 minus sine squared. So cosine is plus minus the square root of 1 minus sine squared. Those are the things we are supposed to know. It just basically is given. plug in. So negative 1/3 to the power of 2 is positive 1/9. 1 minus that is 8/9. So square root of 8/9. You take the square root from the top, you get 2 square root of 2, and the bottom you get 3. And that's exactly what we have here. Okay, so we get to the same answer as expected. Write the trigonometric expression sine of tan inverse of u as an algebraic expression. Tan inverse of u represents an angle and arc. Let it go with theta, and therefore, by definition, tan of theta equals u, and we are looking for sine of theta. All of them in one shot. One more time. You let this be theta. That means tan of theta is u. That means you're looking to find sine of theta. And by the way, I'm reminding you of the sign of various trigonometric functions in various quadrants. A point has coordinates x and y. Remember, x is cosine and y is sine in unit circles. So it will help you see that, of course, everything is positive here in the first quadrant. In the second quadrant, because sine is y, sine remains positive, the rest of them are negative. In this case, the third quadrant, the reason tangent is positive because tangent is sine over cosine. Positive over positive or negative over negative makes no difference. Both of them give us positive. In the fourth quadrant, the reason cosine is positive because cosine in essence is x. So that will help us remember all of that. So with that being the case, let's continue. Cotangent theta, we take it to be 1/u, the reciprocal of that, and we want to find sine. The reason we want to do that because of the Pythagorean identity. 1 plus cotangent squared is cosecant squared. Is one of those that we are familiar with. And so 1 plus, this becomes 1/u squared. So if we put these two together, this is u squared over u squared. In other words, I want to take a LCD and put them together. I get u squared plus 1/u squared. That's the left-hand side. And it's equal to cosecant squared. On the other hand, cosecant is 1/sine. And so if I write the reciprocal of this, I get sine squared. And I write the reciprocal of that. Again, cosecant squared equals 1/sine squared, okay? So what we are doing, we are writing the reciprocal of this. We are writing the reciprocal of that. So sine is plus minus the square root of this expression. And we take it to be positive because sine and tangent have the same sign. The reason is because both of them cover what quadrants? From negative power 2 to power 2. For tangent, the endpoints are not included. For sine, the endpoints, namely minus power 2 and power 2, are included. So I hope everybody's fine with that. Let's look at this methodology, just in case. Tangent is opposite over the adjacent. So if you draw a right triangle and tangent is u, meaning u over 1, and this is theta, the opposite is u, the adjacent is 1. What is the hypotenuse? U squared plus 1 squared, which is 1 under the radical. This is Pythagorean theorem. I hope everybody is comfortable with that. Sine is the opposite over the hypotenuse, which makes it u over the square root of 1 plus u squared. So pretty straightforward, everybody. Reminding you of sum and difference formulas, double angle and half angle formulas, and how we arrive at them. For the sum formulas, I hope you remember, for example, sine of alpha plus beta is sine alpha, cosine beta plus cosine alpha sine beta. And sine of alpha minus beta, if you replace this with minus, you get sine alpha cosine beta minus cosine alpha sine beta. First, we proved the cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. And if you replace the beta with minus beta, it creates this formula: cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine. And tangent, we prove that using sine over cosine. So it becomes tan of alpha plus beta is tan of alpha plus tan of beta over 1 minus tan alpha tan beta. How did we prove tan of alpha minus beta? In this formula, we replace the beta with minus beta. So plus minus beta, and we change that. And remember, all trigonometric functions are even. That means f of, or odd. That means f of minus x is minus f of x, except cosine. So cosine of minus beta and cosine of beta are the same. And of course, with cosine goes secant. So, and tan of alpha minus beta became tan of alpha minus tan of beta over 1 plus tan alpha tan beta. How did we get the double angle? In this formula, if I replace the beta with alpha here, this becomes alpha, this becomes alpha, this becomes alpha. I get sine 2 alpha is 2 sine alpha cosine alpha. I'm reminding you this because in case you forget, this will help you with the memorization. So sine 2 alpha is 2 sine alpha cosine. I want cosine of 2 alpha. Over here, instead of beta, I change this to alpha also. So this changes to alpha, this changes to alpha. If you do that, just right here, if you do that, cosine to alpha becomes cosine squared minus sine squared. Now, if you change the sine squared to 1 minus cosine squared, becomes 2 cosine squared minus 1. If you change the cosine squared to 1 minus sine squared, you get 1 minus 2 sine squared alpha. And tan of 2 alpha, over here, tan of alpha plus beta, change this to alpha and change the beta to alpha, 2 tan alpha over 1 minus tan squared alpha. I'm showing you how we can go from here to here. Now, how do we go from here to ultimately half angles? So from here, we want to calculate sine squared of alpha. Okay, so from here, you get 1 minus cosine to alpha over 2. If you cut the alpha in half, you get alpha over 2, and this becomes alpha. From here, if you solve for cosine squared alpha, you get 1 plus cosine to alpha over 2. If you cut this in half, you cut this in half. For tangent, obviously, it's easier to use sine over cosine, and then all of them are here. When we write them with plus minus, we use the location of a quadrant to figure out, are we going with the positive or negative when we, for example, want to calculate sine of alpha over 2, as an example. So I hope that is clear to everybody. So sine of 195 degrees, and they're asking for half angle formulas. 195 is half of 390 degrees. And please understand, 390 is a common arc because it's 360 plus 30. That's why, okay? That's why that angle is. So in essence, 30 degrees. And so you want to go with the sine of alpha over to that. By the way, that puts you in a specific quadrant, okay? 195 degrees is larger than 180 a little bit. That puts us in the third quadrant. So first and foremost, let me just write that. This belongs to quadrant 3. Why is that important? Let's go to the formula and I'll explain it to you. So sine of alpha over 2 is plus minus the square root of 1 minus cosine alpha over 2. So let's put it in. You have to choose. Is it plus or minus? Quadrant 3. Sine is negative. You choose. First, you put both of them, and then you choose accordingly. Negative. And of course, 390 degrees is the same as 30 degrees. So I hope everybody is clear as to why we have to put this here. This is important. Knowing the quadrants makes a huge difference. All right. So cosine 30, it's a common arc, square root of 3 over 2. If I multiply the top and the bottom, here's what happens. If I multiply the top and the bottom by 2, obviously the bottom is 4 and comes out as 2. This one times this one is 2. This one cancels out. This one gives us square root of 2 minus square root of 3. And don't forget the sign remains. So negative sign remains. This becomes 2. This becomes minus square root of 3. And this becomes 4, comes out as 2. Okay, everybody? Comes out as 2. What about cosine of 15 degrees is cosine of 30 over 2. 30 is a common arc, and this is in quadrant 1. In quadrant 1, everything is positive. We know the answer is plus minus the square root of 1 plus cosine alpha over 2. So using that, plus minus the square root of 1 plus cosine 30 over 2, and we are choosing positive 15 degrees, first quadrant, positive. So that's why. Pay attention to this sign here and what you need to do. That is extremely important, everybody. So you have to make a decision accordingly. All right, so cosine 30 is a common arc, square root of 3 over 2. We've done that, and just multiply by 2. Over 2. Again, the same thing happens. You really get the same answer, but it's a plus sign here. This negative outside doesn't exist either. Very simple. And we're going to move on. However, I want to remind you, you could calculate cosine of 15 as cosine of 45 minus 30. I highly recommend you try that for practice to make sure you have no problem doing it either way in case they ask you to do it that way. We want to prove some identities, secant 2 theta is secant squared theta over 2 minus secant squared theta. When you want to prove identities, you start from one side. And normally we start with the more complicated side. So let's start with the right-hand side. Again, RHS, short for right hand side. Okay, just to remind you, that's what I mean by that. We want to work on this. And normally, one way to simplify things involving secant, cosecant, tangent, and cotangent is to go to sine and cosine. Secant is 1 over cosine. So this is 1 over cosine squared, so is this. This is a complex fraction. So if you multiply the top and the bottom by LCD, which is just cosine squared, should take care of the business. Meaning, I multiply these two, so I get 1. This cancels out this one, right? I multiply these two, I get 2 cosine squared. I multiply these two cancel out, I get minus 1. So I hope nobody has any problem evaluating a complex fraction. It's very straightforward, everybody. So what is the denominator? 2 cosine squared theta minus 1. And we should know that's cosine of 2 theta, right? A various format for cosine of 2 alpha we should know. So this is cosine of 2 theta. 1 over that makes it secant of 2 theta. We want to show that sine cubed theta plus cosine cubed theta over sine theta plus cosine theta is 1 minus sine theta cosine theta. Again, we start from one of the sides. There seems to be the left-hand side is more complicated. We start with the left-hand side. And so at the bottom, there's not much you can do. The top is in the form of a cubed plus b cubed, which is a plus b times a squared minus ab plus b squared. I hope you remember that. Okay, a squared plus b, a squared minus b squared, a cubed minus b cubed, a cubed plus b cubed. Those are the ones that you should know. This is the sum of cubes, very straightforward. So the top becomes sine plus cosine times sine squared minus sine cosine plus cosine squared. And the bottom remains. And by the way, I don't want you to mistakenly think you have a 2 here. You don't. Otherwise, this becomes a perfect square trinomial, and it's not. So these two are identical. We can drop these two. So what you're left with is sine squared plus cosine squared minus sine theta cosine theta. And as you know, sine squared plus cosine squared is 1. One of those Pythagorean identities. And we're done, everybody. We want to solve an equation. When you want to solve a trigonometric equation, if you have multiple angles, this one has 3. So when you have n theta is called multiple angles. The methodology is a little bit different. So I want to go over that. I want to remind you how it's done. First of all, assume this is x or y or z or alpha or beta, and sine x equals 1/2. And that results in 2 answers from 0 to 2 pi, which makes it pi over 6. I hope you remember pi over 6. That's a common R. Sine is positive in the second quadrant, so pi minus pi over 6 makes it 5 pi over 6. So I want to discuss that one because this is also the reference arc x sub r. And in quadrant 2, you put pi minus, remember theta sub r, in this case pi minus, we're using x sub r. So pi minus pi over 6 makes it 5 pi over 6. So I hope everybody remembers that. Okay, so it's very straightforward and you need to know the quadrants. I can't emphasize this enough. So we know the quadrants, we know where sign is positive, and so we are in good shape. Now, x is 3 theta. Let's set it up. 3 theta is pi over 6. 3 theta is pi over 6 plus 2n pi, and then you divide by 3. This becomes theta. This pi over 6 divided by 3, that means pi over 18. When you divide a fraction by a number, multiply its denominator by that number, and this is 2n pi over 3. So that's the case. Also, we have 5 pi over 6. We add 2n pi. Divide by 3, this becomes 5 pi over 18. This becomes 2n pi over 3. And now, because you have multiple angle 3, you start from 0 and you go all the way to k minus 1. 0, 1, 2. Okay, so if you have, if the multiple angle, let's call it k. If the multiple angle is k theta, then we go all the way. So n equals 0, 1, 2, all the way to k minus 1. One might say, okay, what happens if we go further? I'll show you in a moment. What happens if you go, so there's no way to make a mistake. So let's plug in 0, 1, and 2. Let's see what happens. So we are going to go to this one. Replace the n with 0 is pi over 18. And the same thing here. With 0 is 5 pi over 18. But what happens when I put 1 here? So if I put 1, I get 2 pi over 3. So let me write this, everybody. Because this denominator is 18. So I want to write pi over 18 is what? 6 pi over 18. Okay. So if I replace the n with 1, and 2 pi over 3 is 2 times that. So 2 times 6, 12 pi, and pi is 13 pi over 80. If I replace the n with 2, I get 4 pi over 3. 4 times 6, 24, and 1, I get 25 pi over 80. What happens if I choose 3? Just choose 3. 3 cancels out the 3. So instead of n, so you get 2 pi. So it goes beyond 0 to 2 pi. That's why you don't go beyond that. So one more time. If you choose n to be 3, this 3 cancels out, and you get plus 2 pi. It goes back really to pi over 80. Let's do the same thing here. And I give you the answer. For n equals 0, you get 5 pi over 18. For n equals pi 17 pi over 18. For n equals 229 pi over 18. So for this guy, you have how many answers? 2 answers. If it's multiple, whatever this number is, times this. So this has 2 answers. 3 theta has 6 answers from 0 to 2 pi. If we have 5 theta, we have 5 times 2, 10 answers from 0 to 2 pi following this methodology. want to solve this equation. To do so, you look at this one is sine, and then we have both sine squared and cosine squared. Because this is sine, you're going to change this to something involving sine, meaning 1 minus sine squared. So we are changing this one to 1 minus sine squared. We can combine these two. We're going to do with factoring. So we're going to bring, we either multiply by -1 or we move it, however you want to put that, and you put it in a descending order. So when you do that, this becomes positive, this both become negative, and you have 2 sine squared minus sine x minus 1. And factoring is very simple because 2 is a prime number, everybody. So you have a 2 sine x and then sine x. Then because this is 1, you have no choice but to choose 1 in both cases, one of them negative, one of them positive. And how do you check? This is how you check, class. Obviously, this is 2 sine squared, this is -1. You have to check the middle term by saying, okay, the product of these two is sine. The product of these two is -2 sine. Their sum must be negative sine. It is. We are done. It's correct. So either one is 0. That means 2 sine x plus 1 is 0, or sine x minus 1 is 0. This results in sine x being -1/2. This results in sine x being 1/2. 1, my apologies. Now, again, quadrant. The concept of a quadrant is important to remember. So what's going on? Let's first, just in case, if you want to know exactly how to come up with the answer, let's look at the reference arc. Whenever you have a negative, if you can't figure it out, go to the reference arc. Meaning say, okay, I have sine x equals 1/2. I know how to handle that, right? In fact, we just had it in the previous page. X must be power 6. Again, I'm looking at this one. And so what you're looking at, this is called X sub arc. Reference arc is power 6. Now, sine is -1/2. Sine is negative in quadrant. Three. So in quadrant 3 means pi plus the reference arc. And also in quadrant 4, which means 2 pi minus power 6. So we have those answers. Sine x equals 1 gives you power 2. That's easy. So again, I just wanted to remind you how to find the answer if you end up with a negative answer. Just think about the reference arc, and then you can see the answer. All right. Prove the identities. Cosine of power 2 plus x equals minus sine x. We start from one side, in this case, the left-hand side. And we use the fact that we've learned sine of alpha plus beta, sine of alpha minus beta, cosine of alpha plus beta. And of course, we are going to use cosine of alpha plus beta. So cosine of alpha, cosine of beta, minus sine alpha, sine beta, cosine of power 2 cosine x, minus sine power 2 sine x. And we know cosine of power 2 is 0, sine of power 2 is 1. So plug them in. And this goes to 0. This is simply negative sine x. That's the proof. We're done. Tan of theta over secant theta equals sine theta. We start with one side. Left-hand side is more complicated, and we are going to replace tangent and secant using sine and cosine. So we know tangent is sine over cosine, and secant is 1 over cosine. I hope you know when you're dealing with a complex fraction, they have identical denominators. You can drop them. Sine theta is the answer. Sine theta over 1. And we are finished. Or you can just A over B over C over D. You can do these two. Remember that? Put it at top. These two, put it at the bottom. Just however you learn to deal with a complex fraction, that works here as well. We're going to prove the identities cosine to the power of 4 theta minus sine to the power of 4 theta is equal to cosine 2 theta. Again, start with the more complicated side, namely the left-hand side, and use the fact that a squared minus b squared is a plus b, a minus b. Please understand, this is cosine squared to the second, and this is sine squared to the second. So we write cosine squared plus sine squared times cosine squared minus sine squared. This is 1, has no bearing. Cosine squared minus sine squared is cosine of 2 theta, as you know, and we are done. Tan x over 1 plus tan squared x equals sine x cosine x. We're going to start from one side, needless to say. It seems to me the left-hand side is more complicated, and let's start with the left-hand side, everybody. So 1 plus tan squared is secant squared. So just replace the bottom with that. And now we are ready to replace the tangent with sine over cosine, and secant is 1 over cosine, therefore secant squared is 1 over cosine squared. Obviously, the denominator, the LCD is cosine squared, so you're going to multiply the top and the bottom by that. And of course, this becomes sine x cosine x. These two completely cancel each other. We get the right side, sine x cosine x, and we are done. All right, let's move on, everyone. We want to find the exact answer, no need for a calculator. And so we remember sine of 2 alpha is 2 sine alpha cosine alpha. So with that in mind, we can see that this is a sine of 2 times pi over 8, according to this formula, right? And we know 2 times pi over 8 is pi over 4, and sine of pi over 4 is square root of 2 over 2. That is a common arc, everybody knows. It's very straightforward, everybody. What about this one? 2 sine 45 cosine 45. Of course, you can plug in there both, common arc, but that is sine of 2 times 45. Makes it sine of 90 degrees, which is 1. Again, you could just replace them accordingly and you get to the same answer. Each one is square root of 2 over 2, and you get to the same answer, but this is faster. Cosine of 7 pi over 12. It's the same as adding 3 pi over 12 and 4 pi over 12. We're going to use cosine of alpha plus beta. And we should know 3 pi over 12 is pi over 4, 4 pi over 12 is pi over 3, both of which are common arcs. One thing I've mentioned before, and I'm going to mention it again. It's a good idea to know that pi over 12 is 15 degrees. One way you may remember that pi over 6 is 30 degrees, okay? So just in case. All right, so we're going to go with a cosine of alpha plus beta and say cosine of, we're going to use this one, pi over 4 cosine of pi over 3 minus sine of pi over 4 sine of pi over 3. And they're all common arcs. Cosine of pi over 4 and sine of pi over, both of these are square root of 2 over 2. This cosine of pi over 3 is 1/2, sine is square root of 3 halves. Both of them have the same denominator, namely 4. This one, square root of 2 times 1 is square root of 2. These two minus square root of 6. So it's a very simple process, everybody. I hope everybody's fine with that. Cosine of pi over 12, cosine of 5 pi over 12 plus sine of pi over 12, sine of 5 pi over 12. And we should recognize this as cosine of alpha minus beta. So cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta, because it's a plus here. So cosine of pi over 12 minus 5 pi over 12, which makes it negative 4 pi over 12. Now, bear in mind, cosine is an even function, meaning cosine of minus x and cosine of x are the same. So this is cosine of 4 pi over 12, which is pi over 3, and cosine of pi over 3 is 1/2. Cosine of 105 degrees is cosine of 60 plus 45. And that makes it cosine of 60, cosine of 45 minus sine of 60, sine of 45. Right, using the identity. Common arcs. Cosine of 60 is 1/2. This is square root of 2 over 2 minus square root of 3 over 2. And this is square root of 2 over 2 again. All of them, the denominator is 4. 1 times square root of 2 is square root of 2 minus square root of 3 times square root of 2 is square root of 6. It's the same as the previous one, 7 power 12, just for the sake of argument, if anybody's interested. All right, we want to find the exact value of sine 50 cosine 10 plus cosine 50 sine 10. And we notice this is sine of alpha plus beta because sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So this must be sine of 50 plus 10. 50 plus 10 is 60. Sine of 60 is a common arc, square root of 3 over 2. Sine of 165. We can write it as sine of 120 plus 45. We are choosing common arcs, which makes it sine of alpha plus beta, sine of 120 cosine of 45, cosine of 120 sine of 45. That's what it makes. Now, again, I'm reminding you of the different quadrants, and 120 degrees puts us in quadrant 2. In quadrant 2, sine is positive, cosine is negative. And 120 degrees, the reference arc is 60 degrees. So subtract this from 180. That's the concept, okay, to find the reference arc. So this is the same as sine of 60. Positive or negative, we establish is positive. So this is square root of 3 over 2. This is square root of 2 over 2 plus cosine is negative. So cosine of 60 is positive 1/2, but this one is negative 1/2, and this is square root of 2 over 2. So this one is negative, everybody, okay? This one is negative. So be careful with that. Make sure it makes perfect sense to you. And so all of them denominator 4. This is square root of 6 minus square root of 2. So that's why this comes handy. You should be comfortable with that. Again, just remember x and y. X is cosine, y is sine, and that really should help you with remembering the sign is positive or negative. We want to prove the identities. Ln of the absolute value of secant x plus tan x plus ln of secant absolute value of secant x minus tan x equal to 0. And so we are going to start with the more complicated side, which is the left-hand side. We also remember the product rule, which says ln of xy is ln of x plus ln y. Therefore, if I want to go from right to left, ln of xy, that means ln of multiply these two. Now from here, we should recognize that if I move the tan squared to the right, I'll get secant squared minus tan squared equals 1, and ln of 1 is 0. Sine theta plus cosine theta quantity squared plus sine theta minus cosine theta quantity squared equals 2. Obviously, we start with the more complicated side. the left-hand side. So you get sine squared plus 2 sine theta cosine theta plus cosine squared here. Over here, you get sine squared minus 2 sine theta cosine theta plus cosine squared theta. That's what we get. Two sine theta cosine theta and the opposite of that cancel each other. So we have 2 of sine squareds, 2 of cosine squared, and of course, this is 1. So the answer is 2. Very straightforward, everybody. I hope everybody's fine with that. We are going to move on. Solve the equation 2 cosine theta minus square root of 3 is 0, and from 0 to 2 pi, and we want to find the general solution as well. We are going to move this, divide by 2 cosine becomes square root of 3 over 2. So I hope from here to here should be a split second. And so square root of 3 over 2, theta is pi over 6 in the first quadrant. And cosine is positive in the first quadrant and the fourth quadrant. In the fourth quadrant, 2 pi minus pi over 6. So this is clear, common arc we should know. And this one is basically 2 pi minus the reference arc pi over 6. And if you want a general solution, add 2k pi or 2n pi where k is an integer. And by integer, we mean, of course, a set of numbers 0, 1, 2, 2 to infinity, negative 1, negative 2 to negative infinity. That's the meaning of I standing for an integer. Solve this equation, 2 cosine squared minus cosine theta minus 1 equal to 0. You don't have to do anything, just factor it. It's in the right order, descending order. This number is 2, so 2 cosine theta and 1 cosine theta. This is 1 negative, so both of them are 1, one of them negative. So 2 cosine theta plus 1 times cosine theta minus 1. You remember when we dealt with the sign. So you should have no problem with the factoring. Check the middle term. This gives you cosine theta. This gives you negative 2 cosine theta. They do add up to the middle term. So either this one is 0 or this one is 0. So cosine theta is either negative 1/2 or positive 1. So what happens? Again, just to remind you, when you have a negative, think about it as a positive for reference arc. So reference arc is pi over 3. Cosine is negative in the second quadrant. So you write I minus pi over 3. And in the third quadrant, I plus pi over 3. And of course, cosine theta equals 1. Theta is 0. So that's Very straightforward, everybody. So those are the answers. All right. Find the exact value of the expression and justify 1 minus cosine squared 20 minus cosine squared 70. I hope you recognize sine squared plus cosine squared equals 1. So 1 minus cosine squared is sine squared. So that's sine squared. Also, the concept of cofunction, okay, was discussed. Okay. So, for example, cosine of power 2 minus theta was sine of theta. Okay. So, or cosine of power 2 minus alpha is sine of alpha. Well, that means cosine of 70 is sine of 90 minus 70 or 9 or 20. So we can change this to sine squared 20 and they cancel each other. We end up with 0. Cosine 70, cosine 20 minus sine 70, sine 20. I hope you recognize this as cosine of alpha plus beta, which is cosine alpha, cosine beta minus sine alpha, sine beta. So it's cosine of 70 plus 2, which makes it cosine of 90. Cosine of 90, we should know is 0. Tan of 20 plus tan of 25 over 1 minus tan of 20 tan of 25. That means tan of alpha plus beta. Tan of alpha plus beta is tan alpha plus tan beta over 1 minus tan alpha tan beta. So that's tan of 20 plus 25, which makes it tan of 45 degrees. We know it to be 1. Very straightforward, everybody. Sine of cosine inverse of 1/2 plus sine inverse of 3/5. So it's important to understand this is an angle. Let's say alpha. This is an angle. Let's say beta. Okay. So we want sine of alpha plus beta. That's what we are looking for, which we are going to use this formula. So let's look at what we have. When we set this equal to alpha, it means cosine alpha is 1/2. And it's between 0 and pi, remember, because of the restriction on the inverse function for cosine. Okay. We are talking about the first and second quadrant. This one is equal to beta by definition of inverse function. Sine beta must be 3 over 5, and it's in the fourth and first quadrant from minus pi over 2 to pi over 2. Now, we have to calculate from cosine alpha. Okay. We want to go to sine alpha. And from sine beta, we want to go to cosine beta. And so what happens is that this is cosine alpha, and you want to find sine alpha. Sine alpha is positive in the first and the second quadrant. This is first and second quadrant. And since sine squared plus cosine squared equals 1, okay, so we're going to use that, sine alpha cosine beta plus cosine alpha sine beta. That's the formula. We need to find from cosine alpha, as I mentioned, sine alpha, and from sine beta, cosine beta. So sine squared plus cosine squared equals 1. That means we should know sine alpha is square root of 1 minus 1/4. I'm assuming by now we have mastered the beauty of Pythagorean identities and we know how to go from one to the next. The reason this is positive because this is quadrant 2, everybody. All right. So that's 3/4, and it comes out as square root of 3/2. Cosine of beta, sine beta takes place in the fourth and the first quadrant. Therefore, cosine is positive because cosine is positive in those two quadrants. So square root of 1 minus sine squared. So 1 minus 3/5 squared is 9/25, which makes it 16/25, which comes out as 4/5. And so let's write a summary for what we have here, everybody. We put everything that we have in this table just to make it easier to follow and plug in. That's the reason you don't really have to. We have 4 numbers that we are interested in: sine of alpha, cosine of alpha, sine of beta, cosine beta, plug it. That's the idea, everybody. So both of them have the denominator 10. This is 4 times square root of 3. This is plus 3, and we're done. It's that simple. We want to establish identities tan theta plus cosine theta over 1 plus sine theta equals secant theta. We start with the more complicated side, namely the left-hand side. So we change everything to sine and cosine, which means tangent theta will be changed to sine over cosine. And this is fine. And now the common denominator is the product of these two. Cosine theta times 1 plus sine theta is the common denominator. So this one, sine theta times 1 plus sine theta gives us sine theta plus sine squared. And these two, cosine squared. Using LCD to add 2 fractions. So I hope nobody has any problem with that. So we can add 2 fractions easily. And as you know, these two sine squared and cosine squared, they add up to 1. Sine theta plus 1 is the same as 1 plus sine theta. They cancel each other, so we get 1 over cosine theta, which is secant theta. And we proved the identity, everybody. Now sine of 3 theta over sine theta minus cosine 3 theta over cosine theta. We want to prove it's equal to 2. Again, we start with the more complicated side, the left-hand side. We take a common denominator of sine theta cosine theta, and we multiply this one by this one. We get sine 3 theta cosine theta minus, we multiply these two. We get cosine 3 theta sine theta, in any order you want to write. Here's what we notice. Sine alpha cosine beta minus cosine alpha sine beta, that's sine of alpha minus beta. And this one, we remember sine of 2 alpha is 2 sine alpha cosine alpha. Therefore, this is half of that. So this one follows this formula, becomes sine of 3 theta minus theta. And this one, let's put a 2 and 1/2 next to it to make sure we understand. This is sine of 2 theta. Okay. This is also sine of 2 theta. You get 1 over 1/2, which is 2. So pretty straightforward, very simple. I hope everybody's okay with that. We continue with establishing identity 1 minus sine squared over 1 minus cosine theta is minus cosine theta. We start with the more complicated side, the left-hand side. A couple of different approaches. One is to take a common denominator, and I will look at that in a moment, but you may notice this is a squared minus b squared, because class 1 is 1 squared, 1 cubed, whatever you want it to be. So you can say 1 minus cosine theta, 1 plus cosine theta, and therefore you can drop this. So this is gone. 1 minus the parentheses. So 1 minus the parentheses, which makes it 1 minus 1. Let's write. And you're done. So negative cosine theta. If we take a common denominator, that works out the same way, just quickly. So change this to 1 minus cosine theta over 1 minus cosine theta. So we get 1 minus cosine theta, and apply the negative sign, minus 1 plus cosine squared over 1 minus cosine theta. So what you're looking at, 1 and negative 1 cancel each other. So you have cosine squared minus cosine theta. If you factor the cosine theta from the numerator, now what happens is that these two are opposites. When they cancel each other, they create a negative sign, and that's important to know. You get minus cosine theta. I thought that's interesting to say it both ways, okay? Ultimately, it's up to you. Sine theta plus cosine theta over sine theta minus cosine theta minus sine theta over cosine theta is secant theta cosecant theta. Clearly, the left-hand side is the more complicated side. And most of the time when you're dealing with fractions, LCD, and you're adding up, subtracting, and so forth, LCD will do the job. Clearly, LCD is the product of these two, sine theta, cosine theta. In any order. And so we're going to multiply this one by this one. We get sine theta cosine theta plus cosine squared. minus, we're going to multiply these two. That gives you sine theta, cosine theta, minus sine squared. This negative will change the sign. Please understand one more time. So this was easy, sine theta, cosine squared. This one, sine times cosine with a negative sign. Sine times negative sign minus sine squared with the negative sign becomes plus. And these two are opposites, drop it. And you're left with cosine squared and sine squared in the numerator, they add up to 1. The reason I put cosine theta first, everybody, so 1 over cosine theta times 1 over sine theta, and 1 over cosine theta is secant theta, 1 over sine theta is cosecant theta, and that's exactly what we have here. So that's why I put the cosine theta first. Establish the identity sign of 4 theta is cosine theta times 4 sine theta minus 8 sine cube theta. It's an interesting question. I want to actually look at it both ways, starting from the left and then starting from the right, just for the sake of argument, so you've been exposed to that. So the left-hand side, sine of 4 theta is sine of 2 times 2 theta. That's the approach we're going to take. So imagine this is x. This is something, x. Sine of 2x. Or sine of, or alpha. Maybe it's easier because you have the formula. So 2 sine alpha, cosine alpha. So this is 2 sine 2 theta, cosine 2 theta. That's the idea. So we use that. Each one will be changed. Sine of 2 theta is 2 sine theta, cosine theta. Cosine of 2 theta, we are going to use 1 minus 2 sine squared. So this, of course, becomes simply 4. 4 sine theta, cosine theta. And this is 1 minus 2 sine squared. Remember, we want it to look like that. So cosine theta, keep it, and 4 sine theta, put it next to that. So we are just interchanging these two, and now we are going to multiply. If you multiply, you get 4 sine theta minus 8 sine cubed. Take a look. Sine of 4 theta is now cosine theta times 4 sine theta minus 8 sine cubed. We just proved that using the left-hand side. Let's look at the right-hand side and prove it. And the reason I'm doing this, because one may find one easier than the other. It appears the right-hand side is more complicated. So let's go with that one too. And the process is, from the parentheses, you take a common factor of 4 sine theta out. If you take this one out, you get 1 minus 2 sine squared. And so just rewrite this as 4 sine theta, cosine theta. And this is 2 times 2. So 2 times 2 sine theta, cosine theta. So 2 we keep, 2 sine theta, cosine theta. Sine of 2 theta. 1 minus 2 sine squared, cosine 2 theta. So this one is sine of 2 theta. This is cosine of 2 theta. And so going back to that, this is 2 sine alpha cosine alpha. That means sine of 2 alpha. The alpha is 2 theta. So think about 2 theta, everybody. Think about 2 theta as alpha. And again, think about this. And you get sine of 2 times 2 theta, which is sine of 4 theta. And again, I'm not too sure which one is easier for you. You decide. Either way is fine. Just a brief coverage of this concept. Use the product to sum formula to fill the blanks in the identity. Sine of 14x cosine of 6x is half of sine of something plus sine of something. These are the theorems that gives us the product to sum. And if you compare all those three, you see this is identical to that. Sine alpha this is alpha, cosine beta. That means 1/2 sine of alpha plus beta, add them up. And then sine of alpha minus beta, 14 minus 6, 8x. And so this is replaced with 20x. This one is replaced with 8x. And that's the final answer. And that was just an example of the product. So